We're grateful to JILA for their partnership for today's experience, as well as JILA's Team for Excellence in Diversity and Inclusivity. And I love that the abbreviation for that is JEDI. Thank you everyone for being part of this experience. And here's a roadmap of today's program. With introductions of our speaker, Olivia, and members of our team today. Once we've gone through introductions, Olivia will then take the floor and deliver this fabulous STEM chat. Each of you will then have your opportunity to ask Olivia questions. All questions are good questions. Ask her about her day in the life of being an astrophysicist. Ask her about her day in the life of being a graduate student. Ask her about when she was young, when she was your age. No matter what you ask, it's a good question. We'll ask you to post your questions in the chat, and then we'll call on you so you can directly ask your question of Olivia. After we do the Q&A, then we'll gather your words and phrases on your favorite parts of today's experience. We'll ask you to put those in the chat as well, and then Crystal will collect all of them together and put them into a beautiful word cloud that we'll send back to you. So, what I'd like to do now is to introduce you to our co-host for today, as well as to the She Has the Floor series, B. Petner. So as I introduce you to B, I want you to imagine what it would feel like, and maybe some of you already know this, to have everybody telling you what they think you should do with your future. What would you do if you had, or maybe do have, a great brain for math and engineering, but your heart is really in another place? What would you do if you were officially on the path to becoming an engineer, but you wanted to leave engineering to do something that your heart had been set on since you were in elementary school? Well, that's what happened to B. She was on the path to becoming an engineer. She graduated from high school at age 15 and at the same time earned an associate's degree in math. And today, she's not an engineer. She's fulfilling her lifelong dream of being a fashion designer. And everybody should know that fashion design has everything to do with science and math. B, you have the floor.
Thank you so much, Heidi. I want to start by referencing some quick guidelines in the chat. The first is to mute your sound when you are not speaking. We would love to, if you can leave your camera on if possible. Also, please make sure you have good internet connection, and if you can change the Zoom name to your name if you're using someone else's account. Also, as Heidi mentioned, when we get to the Q&A portion, to place your questions for Olivia in the chat. We will then gather the questions and call on you to pose your question to her at that time. Every question is a good question. Please ask questions. And when asking your question, say your name, where you're from, and as appropriate, your grade level. With that, I'm excited to introduce Gail. Gail Geschwind is someone who loves to participate in outreach programs that make a positive and meaningful impact in others' lives. This is what she did when she helped found JEDI, JILA Excellence in Diversity and Inclusivity, a group which helps promote diversity as an integral element of a collaborative research institute. JEDI functions alongside her work as a graduate student in the physics department at CU Boulder, where she does a single molecule biophysics research, focusing on the mechanical and energetic properties of nucleic acid structures. Gail received her Bachelor's of Science in Physics and Math from Stony Brook University, New York. Gail, over to you.
Hi, everyone. Thanks, Bea, for the introduction. So I'm Gail. And like Bea said, I'm a graduate student, and you can kind of think of that like I'm in 21st grade. So, I went to middle school and high school, and then I went to college. And then after I got going to college, I kept going to school, and I'm still here, so 21st grade. And I work in JILA studying biophysics. JILA is a collaboration between CU Boulder, which is a college, and the National Institute of Standards and Technology, which is a government lab. And there is so much really cool research happening there. So there's people studying astrophysics and lasers, atoms, molecules, and there's even people making the most precise clocks in the entire world. And like you said, I'm also involved in JEDI, so JILA Excellence in Diversity and Inclusivity, and we work on making sure we have a diverse environment at JILA, and that involves making sure we get more girls interested in science. So one of our most important messages is that science is for everyone, and I hope that you guys can all see yourselves as scientists. And I know that you're going to love today's talk, but before we get to that, I'm going to turn it back over to Heidi.
We wouldn't have a program today if it wasn't for some really amazing people, including JILA and JEDI, but I want to run through a list of those to whom we owe a lot of thanks. The Deaver Phoenix Foundation, HP, the Community First Foundation, the Women in Science Network at Colorado State University, Gabby Communications and Ruth Pankratz, Toolbox Creative, Tom Campbell and Dawn Putney, Payroll Vault and their great team here in Fort Collins, Colorado, Prima Productions, and of course, as I've said already, JILA and JEDI. Thank you to Jane Hamburger, Marianne Heyman, Russ Harrell, Doug and Judy Brobst, and donors who make She Has the Floor and other of our programs possible. And now, as we begin, we have a question for all of you. We live in the Northern Hemisphere, and so here's the question that we want to pose to you right before we introduce Olivia. We're in the Northern Hemisphere. Why are fall and winter the best times of the year for looking at stars and planets in the night sky? So this is a multiple choice question. So I'm guessing that everyone can see that because some of the votes are already coming in. Cast your vote in the Zoom poll on your monitor. There are 3 possible answers. Okay, is there anyone who has not voted? If you need a few more minutes, let's just take 1 more minute for this, or if you think you want to change your answer, let's take until 4:40. So 1 more moment, and then we will announce the real answer. And adults, this is for you as well as the girls on the call who are the future scientists and astrophysicists. Okay, does anyone need more time? All right. Okay, who thinks that they are sure of this answer? Put your hand up if you are confident about what you had to say. Okay, all right. Okay, we've got a few confident people. All right. Let's share the results of this poll. And can everybody see that? Okay, if you answered question number 2, put up your hand. Okay, all right, question number 2. Okay, wonderful. So actually 3 people, it looks like, answered number 2. And if you answered number 3, put up your hand. Anyone for number 3? Okay, Tom got number 3, Charlotte. All right, so if you answered number 2 or number 3, you're correct. Those were 2 different ways to get at the answer for this question. Yes, the fall and winter nights are longer because of the change in seasons. That's one possible answer. Yes, that's correct. Also, number 3, Earth's axis is tilted so that the North Pole is pointing away from the sun and the sun is falling indirectly on the North Pole. So if you answered either 2 or 3, you're correct. All right, so in conjunction with this, we have an activity for you that we want you to know that you can keep doing throughout the month of November. So Crystal's going to put some directions in the chat, and I'll just walk through this with you. Now that you know why it is that winter and fall are so great for sky watching, we want you to do this. First, borrow a pair of binoculars if you can. Go outside before 6 p.m. Tonight in Colorado, anyway, in northern Colorado, where we're coming to you from, sunset will be at 5:57. So go outside before 6 p.m. and face toward the setting sun in the west. You want to look low in the sky with your binoculars, and just as the sun is setting, right to the left of the sun, you'll see a bright, dazzling spot, and that is the planet Venus. And so look through your binoculars, especially come this Sunday and Monday. When you look through the binoculars, actually you'll be able to see the moon rising and passing right across from Venus, and you'll see Venus and the moon in the same set of binoculars. The next thing to do then is to keep watching throughout the month of November. November is a great time to watch Venus, because as the month keeps marching forward toward the holidays, you'll see Venus rise in the western sky. And so that's our star gazing and planet watching activity for you for the month of November. All right. What I'd like to do now is turn it back over to B, and she's going to announce our speaker for today.
Thank you. So maybe some of you have been the only female in one of your classes, and if not, perhaps you can imagine what that might feel like. Can you imagine being the only female in your graduating class to receive a bachelor's degree in physics? Well, that is what happened to Olivia Krohn, who attended California State University in Fresno, where her undergraduate graduating cohort was so small that she was indeed the only female that graduated in that graduation to receive her Bachelor's of Science in Physics. Now, Olivia is a PhD student at the University of Colorado Boulder, where she works in the Lewandowski group with JILA fellow Heather Lewandowski, studying molecular collisions in cold, low-pressure environments. This work combines Olivia's interest in investigating the fundamental dynamics of molecular reactions, as well as investigating chemistry that occurs in outer space. Today, Olivia will be talking about experimental skills and the amazing chemistry of our outer space, with her many experiences and successes. And now, with that, she has the floor.
Thank you, B. Thanks everyone for being here. I'm really excited to be here today. I really like talking about research, and this is a lot of fun to me, and it's fun to see you guys here as well. So like B said, I am at JILA, I'm in the Lewandowski group, and I'm actually in the same class as Gail. So I am also in grade 21. So that was a really nice introduction that Gail gave for kind of where I'm at in my school as well. And yeah, I'm going to be talking about experimental skills and the amazing chemistry of outer space. So the first cool thing is the background I get to use today is one of the pictures that I love using when I talk about research. And I don't know about you guys, but this sort of picture, these amazing, beautiful pictures of outer space and all the stars and lights have always really made me feel full of awe and kind of this desire to ask questions and try to find those answers. And I was thinking about how long that space in particular and science have really been cool and interesting to me. And I was realizing one key moment I remember that really got me excited about this area was when my family was able to go on a vacation to Florida to Cape Canaveral, where NASA has launched a lot of its satellites and shuttles. And I talked to my dad and actually found some pictures, and this happened when I was 12. So here's pictures of me and my sister on the left here. I am 12, this is my sister Emmeline, she was 9 at the time. And we were super excited to see these shuttles, and there were simulations and museums. And I remember that making me really excited about space and engineering and science. And I think when you find things that you love learning about, it's worth really leaning into that, because oftentimes we have to learn things that are really hard to learn, and it's a lot of work. And it's still work when we love learning about it, but I find that it's a lot less work and it's a lot more fun. This picture of me on the right is when I was in college, so a couple years ago. And at the time, I actually wasn't studying what I'm studying now at all, but I still found out there was a space shuttle in Los Angeles where I was working at the time, and I had to go see it because it was still just so exciting to me. So maybe it's not surprising I came back to this area. Now, what did my experiment actually look like? I don't know about you guys, but I don't think 12-year-old me would have thought a space experiment would look like this. I think it kind of looks a little bit more like a spaceship, honestly. It's shiny and made of steel, and there's a lot of parts in there that just don't really make sense to, would not have made sense to me why they were important for being able to study chemistry that happens in space. But it's been really cool, and the things I've learned how to do have been awesome. So what I'd like to do today is back up a little bit and talk about what I even mean by space chemistry. What do people that study that, what are they even interested in? And then I'm going to come back to this picture and talk a little bit more about what's going on in this experiment and why those parts are so important to do what we want to do, and kind of how that has formed my journey of learning how to become a scientist. So let's do that. What is space chemistry? What do we even mean when we talk about chemistry in general? And I know, depending on where you guys are at in school, you may have heard a lot or only a little about what chemistry even is. So I'm going to sort of try to give us all a background on what I mean when I say chemistry and space chemistry. And if I'm not clear, if I jump too far and I'm confusing, I hope you guys ask me more questions so it's more clear to you. And if I give way too much basic stuff and you want to hear more about something, please ask for more details as well. I'm going to try and bring us all on the same page there. When people talk about studying chemistry, I find that there's kind of a key thing that all chemists were trying to understand. And that is, if you take anything, any material, our shirts, food, screens, our skin, hair, and you start chopping it down into smaller and smaller bits. The idea is that if you keep chopping anything down into smaller and smaller bits, at some point you get to something super fundamental. It's like a fundamental building block. And the way that that building block behaves starts to impact how all the bigger pieces behave. It's kind of like saying that the universe, if you start chopping it down, there's a building block like a Lego. And so chemists have essentially found these Legos that you can't divide that make up everything, and they call them atoms. And they organize them into a super tidy, cool looking table. And all of these atoms behave differently. The way that they want to react with each other, or the way that they want to stick to other things or don't, will make up, will kind of determine how they act as bigger materials. So the idea is, if you study these atoms and you study what they do when they start interacting and building with each other into bigger things called molecules, then you can start to understand all of the big scale things that we see in the universe. If you start to understand these atoms well, then you can figure out how to make screens brighter and clothes softer, and how to keep your skin from sunburning, and how to make food taste better, and all these other things that follow from these building blocks. And I find that this is sort of at the heart of what all chemistry is really about, is understanding the small bits so that we can understand the big picture stuff. So how does this interact with space chemistry then? Well, space is full of molecules. It's full of combinations of these atoms. This is supposed to be an overwhelming list. This isn't supposed to make any sense. And this is only like a quarter of the number of molecules that people have found. And the main thing I want to say here is that there's a lot of molecules in space, and that this is actually kind of surprising. And it's surprising because space is kind of empty. And I'm going to get back to what I mean by that. But for a moment, I want to talk about one molecule, and I'll kind of explain what I mean by that using this molecule. So I'm going to pick this one right here. And I'm picking this one because this is actually the one I study quite a lot with. And we're going to take a look at it. So this molecule is actually built up by taking 4 of the building blocks, taking 1 nitrogen and 3 hydrogens, the white ones here. And these are actually atoms that we find all over in our air. And so if you combine them in this way, you get a molecule called ammonia. And this is a molecule that we know is in space and that people are very interested on how we can make it. Now, how do you actually make a molecule? Well, I know as I think about it, it seems like maybe it's something like, you know, you take a nitrogen and then you take a hydrogen and let it stick on, and then you take another one, let it stick on, and another one, let it stick on, and then you make ammonia, right? Well, that's actually kind of how a lot of chemistry works. Some chemistry happens, you know, some in a lab coat in a beaker. Some chemistry happens in the kitchen. A lot of chemistry happens all over nature. A lot of chemistry happens in the air we breathe. And when we look at chemistry that happens just in the air, it's actually a lot like this. You have a nitrogen atom that just bounces around, and you have another atom that comes and they hit each other, and sometimes they stick and sometimes they don't. And the times they stick, they start building up into bigger and bigger molecules. But here's the thing about that. If you're gonna build molecules by having them just collide into each other and stick, they need to be colliding a lot, or it would take forever to make molecules, right? But here's the crazy thing about space. These things don't collide very often in space. Now, if you were to think about like taking a deep breath, the amount of air you suck in has tons of atoms and molecules in it. In fact, the number of molecules in like one lungful of air is this. That's 24 zeros. Guys, I don't know how to say this number. I think it might be a billion. It might be bigger. It's a really big number. In fact, maybe a better way to think about this is in just the space of a lungful of air, every time you blink, you have collisions of atoms running into each other hundreds of thousands of times. In contrast, if you were to take in a lungful of space, you might have to go hours or days before you have 2 atoms run into each other. And so you can imagine that in space, it takes forever for things to be able to collide to each other and have opportunities to build into bigger molecules. So now the list I showed you guys earlier is actually a really cool puzzle because it takes so long that the questions of why we have so many molecules and why we have some and not others has a lot to do with what kind of molecules want to react with each other and what ones don't. And so by studying those reactions, we understand a lot more, not just about chemistry that happens in space, but about chemistry of any kind of molecules, how they like to behave and how they like to react with each other. So, sorry. That brings me to kind of my first big question. And I think part of science is just asking questions and searching for the answer. So the first big question of my research is, how do we get from those small atoms to the big molecules? And how long does it take? Can we study some of these molecule collisions and figure out which ones react and how long that takes? And then another big question I'm working on is, when the molecules do react and stick, are they more likely to build bigger molecules when they're moving really fast? Is it something where like the more they collide with lots of energy, that makes them more likely to make bonds? Or is it better for them to go slow? Are they more likely to form an attachment and not just bounce off of each other if they're going slow? So those are the 2 things that I am trying to study in my research. So coming back to that picture of my experiment, all of this experiment is actually just trying to get at those 2 things that we're trying to look at. So in one side, we've got this, what's called an ion trap. So we take some of these ammonia molecules and we get them all charged the way that your hair is kind of charged up if you rub a balloon on it. And we use electricity to shove these atoms, these molecules, into as small a space as we can, right in the center of this trap. And then we bring lasers in on the side, and these lasers help cool down those molecules as cold as we can get them. And the rest of the part of the experiment over here to the right is actually just trying to bring in a string of molecules at a controlled speed so that we can bring them in and have them intersect right in that middle of the trap and either have them going really fast or really slow. And in doing that, we have them interact in a really small space, and then we can see how likely they are to make bigger molecules depending on how fast the other molecules are going. And what's crazy about this is, of course, it's a big experiment for just a really simple reaction, right? But that's what it takes to be able to control those speeds and the identities of the molecules we're studying really carefully. And that means there's a lot of skills that I've had to learn to be able to do this. So for example, that trap I showed you has got all these wires on it. And these wires are electronics that are very carefully controlling electricity so that we can push these atoms into the very center. And that leads to some big and complicated boxes like this one in the center of my screen. To do this experiment, I've had to learn how to build these chambers in a way that makes sense and allows us to do this experiment, and to work with lasers that are bright and powerful and have all these mirrors and lenses so that we can really carefully change the color of the laser to do the types of science we want to do. And one thing that's really cool about this is I've had a lot of challenges of learning how to do things that I didn't know I knew how to do. It was just something where in lab, I was like, oh, we got to figure this out. And then I and my lab mates will just have to figure out how to do it. And you learn some really cool things that way. And I think importantly, you learn that there are things you can do that you didn't know you could do. There are challenges that when you face them, you're able to overcome them. But sometimes it's more challenging than that. Sometimes you don't always figure out how to fix things either. So this particular picture, this electronics box, was actually from Thursday. And this thing was broken, and we were really hoping to fix it because it would have allowed us to do something cool with our experiment. But yeah, I couldn't figure out how to fix it. And sometimes this can be really challenging because, you know, when we try hard things, we don't always succeed. Sometimes things are too challenging, either for where we are at the time or for where our skills are. But I've come to believe that that's not a bad thing. When we're challenged by stuff and we sometimes fail, I think that's a good sign that we're challenging ourselves to do hard things. Because if we're not challenging ourselves and always doing easy things, of course we're always going to succeed. But when we grow and try to learn new things, sometimes we won't succeed, and that's okay. Sometimes things are too challenging. But there's another thing that sometimes makes science a little hard, and I think this is a safe place to sort of talk a little bit about this as well. As Bea said in the introduction, that I was the only girl in my graduating class to get my bachelor's. So this can sometimes be a little bit lonely. I don't know if you guys have ever tried to do something and you felt like either you were sort of alone in what you were trying to do, or maybe you felt that other people around you thought things were too challenging for you, even though you knew it wasn't too challenging for you. Sometimes I find science is a little bit like this for us as ladies. Sometimes people look at us and make assumptions and think things are going to be too challenging when really they aren't. And this can be really discouraging because sometimes it already is hard, and it's really easy to get discouraged even when we can do great things. And this of course makes things more challenging. But I was thinking a lot about this and thinking back on my journey becoming a scientist, and I realized that a lot of the reasons that can be very hard is because the people around us have a very large impact on us. When people don't believe in us or people think we're limited, that can be really, really discouraging because it often matters to us what people think. And I think that actually can work for us in a positive way as well. When people believe in us and they see our potential and they cheer us on, that gives us courage to try really challenging things. And so I want to add a picture to this. And this is a picture of these two ladies. And even though technically one was not in the same degree and one graduated later, we still shared some classes together and shared a lot of the celebrations. And it was a way that we were, even though we weren't sort of on the exact same path, we were still able to encourage each other in the things that we were individually doing. And in fact, this goes much broader than just these two friends that I show on the screen. there are a lot of people in my life that have believed in me and encouraged me and rooted me on, even when I would get discouraged or sad or challenged by science. And I think this is really important because sometimes when we do hard things and don't succeed, we're tempted to think we don't belong or we should stop trying. And I think the reverse is true. It's often the case that when we're challenging ourselves, it actually means that we are growing and we're finding something we love. And so leaning in and listening to those people that do see us and do know that we can do it is really important. And being able to be there for those people and to see what they can do and tell them that they can do it is really important for all of us to be able to grow and push ourselves. So a lot of the people on the screen have, and more people too, honestly, have been the people that even when I've thought, what am I doing in science? Maybe I can't do this. There are so many other things. They've been people that have sort of pushed me to continue to grow and remind myself that I really love doing this and it's worth it. So that's kind of what I wanted to share with you guys today. If you would hear just to find things that you love to learn, that science is all about asking questions and looking for the answers, that space chemistry is cool, and that finding people that encourage you and believe in you and being able to encourage them is a really important way for us to be able to overcome challenges, not just in science, but in all of our life. So with that, I'd like to turn it over to questions with this serious face here.
Thank you so much, Olivia, for that equally interesting and inspiring talk. That was wonderful. At this point, we're going to open it up to questions. So as a reminder, please place your questions for Olivia in the chat function. Heidi and I will then gather those questions and call on you to pose your questions to Olivia. Please take part, ask questions. Every question is a good question. And when we call on you, unmute yourself. And when asking your question, say your name, where you're from, and as appropriate, your grade level. So as the questions start to come into the chat, I'll just kick it off with one to Olivia. What is your day in a life of a scientist like? What does your typical day look like?
Yeah, thanks, B. That's a great question. It's different a lot of days. So right now, we sort of finished building up that picture you saw where I was building that apparatus. We finished building it. But what we have to do right now is make sure that that chain of molecules that can come in at different velocities, we have to make sure we really understand what speeds they're coming in, how many of them there are, so we can understand the data when we take it. But right now we're having to do a lot of upgrades to the experiment to make sure we get enough of them. So it usually looks like I come in and I turn on lasers so they're nice and warm, and I turn on electronics, and then hopefully everything looks happy and great, and I can just start basically kind of taking pictures of these molecules as they come out of these chains and make sure they look good. Usually what ends up happening is I have to add a new part to the experiment. So I have to go find some power supplies and go find some electronics that do what I want it to do and figure out how to hook it up to the computer so the computer can tell it what to do and have it all automated. And then something goes wrong and I have to figure out what that is and fix that. And then usually over a couple of days, I add something new and I sort of work out the challenges with that things that aren't going right. And once that starts going right, then I try to understand the output again. So it's a lot of little things. I hope that made sense.
So Olivia, Althea would love to know, when did you decide you wanted to be a scientist? And actually, I need to let her ask that question. So Althea, please go ahead and unmute and please go right ahead.
Okay, I'm Althea. I'm in 6th grade, and I am wondering when you decided that you wanted to become a scientist.
Thank you, Althea. That's an awesome question. Not for a while, actually. I always knew I liked science and math, and I really liked space. I think for a while I thought I wanted to be a math teacher. And then in high school, somebody told me people that like math and science do engineering. So I thought I'll be an engineer. And then my high school physics teacher was supposed to write me a letter of recommendation for colleges for engineering. And she said, no, you should be a physicist. You should be a scientist. And I was like, what do physicists do? And my parents have basically helped me figure out like, what is engineering versus physics? What is a scientist, you know, and all that. And I think the line is a little bit blurry there too. Plenty of engineers do science as well. But I realized what I liked about math and science was asking these questions and looking for answers. And I think that was the moment where I realized, yeah, that's exactly what I want to do. And I want to find jobs that look like that and pursue that.
Next, Lucy, if you want to unmute yourself and ask your question.
Hi, I'm Lucy. I'm 6th grade. I was wondering what one of your favorite experiments was.
Ooh, thank you, Lucy. That's a great question. I hope it's the one I'm working on now. So let's see. One of the experiments I worked on before was a little bit like the picture I showed you, where you trap some of the molecules in a super tight place. And then instead of bringing them in at a controlled speed, we just let them all come in kind of at a really high speed and just interact. And we did that with 2 molecules that I thought were pretty cool. And they were called acetonitrile and carbon chlorine plus. And one thing I really liked about that experiment is I actually got to do some of the modeling for it. So we had this computer software that could try to predict how these molecules were going to interact and where the bonds were going to be formed. And one thing that was really cool about that is I was able to use this computer model, and it actually agreed really well with what we saw in the experiment. And I felt like I got to understand more than normal. I got to understand more of what was happening with the chemistry in our experiment. And that was really cool. But I'm hoping it's the one I'm working on now, the pictures I showed you, because it's really hard to control the speed of molecules when you're looking at those reactions. And if I'm able to succeed in that, we'll be one of the first people to do it for the energies we're doing, which I think is really cool. So I think it's my favorite right now, but I'm hoping things don't break. Thank you, Lucy.
Althea, please go ahead and ask your next question.
How long would it take to like build and set up such a big experiment like that?
That is a great question, Althea. I think I'm going to pull up a picture of the experiment so I can point to different parts. So that's a good question, because this experiment is not just from me, it's from other people that have worked on it too. So can you guys see my cursor, my pointing?
Yes,
so,
we can see it.
Okay, great, thank you. This part of the experiment right here, what my old lab mate worked for this on 4 years. You can build it I'll come back to it. So you spend 4 years like really understanding this really well so that we can do the best science we can on it. And this part right here, different people have worked on it for 8 years. So this whole thing here, for as well as it can work, was a long time and a lot of people's really hard work. And I kind of have been able to take what people have worked on one side and another side and bring it together and build the parts that it needs to combine it. The work that we had to do to build it up and combine it is something we've done over the last year. So that part has not been so long, but for people to design all the electronics and the lasers that have been necessary to do this is actually a lot longer and a lot of people's hard work.
Olivia, you talked a lot about challenges in your STEM chat. Eleanor Roosevelt once said, "You must do the thing you think you cannot do." And I'm paraphrasing there.
Mhm.
Just give us a summary of why you think we do the things we think we cannot do. You referenced sometimes you experiment and it just doesn't come out.
Mhm.
So why why set ourselves up for doing those tougher things?
Yeah, thank you, Heidi. That's a great question. I think if we don't try to do things that we think we can't do, then we limit ourselves to only the things we think we can do. And that's kind of a wordy sentence, but basically, if we believe, oh, I can't do that, therefore I shouldn't try, then we'll never know if we actually have more capability and more skill than we think we do. And that means we're letting ourselves be more limited than we actually are. And there are so many great and amazing things that we can do, you know, and if we never get a chance to try, then we'll never know that we could have done them.
Thank you. And now I want to invite everybody just to take a moment to reflect on what Olivia has presented and for the whole span of time that we've been together, and capture what your favorite part has been in a word or a phrase, and please put that in the chat. And I want to say too, if you have more than one word or phrase you want to pop in there, if there was more than one takeaway, please put it in there. And again, we'll create all these into a word cloud, and we'll let that be a surprise what the shape of it's going to be, but it'll be really cool when you receive that. So.
And at this point, a final few announcements for the evening is to please join us again on November 16th for the link between molecules in space and life on Earth. Our speaker will be Rebecca Hirsch, an astrophysicist exploring the boundaries of space. We'd also like to say a huge thank you to Olivia for your wonderful presentation and questions and your inspiration, to JILA, to JEDI, JILA Excellence in Diversity and Inclusivity, and to everyone who attended today. Also, a huge thank you to our great team at Pretty Brainy, including technical director for this program, Crystal Bordner, our content creator, Kenna Castleberry, social media maven, Amber Cruz, number cruncher, Jessie Ann Lee, ambassadors, Katie Shute, Madsy Boyle, and Emma Younger, and our board members, Mina Bogopal, Don Putney, and Robin Steele. From Heidi and myself, thank you all so much for attending tonight, and we hope that you have a lovely rest of your night.